A couple of technical identities. The first one is going to be Schwarz inequality. And suppose we have two wave functions, say psi and phi. So let's create a new wave function called chi, and that's going to be given by psi minus the inner product between phi and psi divided by the norm squared of phi. So we are assuming that phi is not necessarily normalized, times phi. So now we know that since chi is a wave function, that its inner product with itself is greater than 0. So if we now expand this, we're going to get 4 terms. So the first term will be the inner product of psi with itself. The second term is going to be the inner product with phi with itself, but it's going to have the coefficient, the phi psi inner product norm squared divided by phi norm to the power 4 inner product of phi times phi. So this is coming from square of this term. The cross terms will be something like phi psi divided by phi squared inner product of psi and phi, and another term which is very similar but with psi and phi interchange in the numerator. So we have psi phi and then phi psi inner product divided by phi squared, and this whole thing will be greater or equal to 0. Right, so now in the second term we see that this guy is nothing but phi squared, so we can do that. And so as a result, we are going to have psi, the inner product of psi with itself, and then we are going to have inner product of psi phi squared divided by phi squared. And then we are going to have these two terms are the same. So we are going to have minus 2, the mod of the inner product of phi and psi squared divided by phi squared, and this is greater than 0. So now these two guys are also the same. So as a result, we have the inner product of psi is greater than the inner product of phi psi squared by phi squared. And as a result, we get the inner product of psi, the inner product of phi. The product is greater than the modulus of the inner product between phi and psi. And this is Schwarz inequality. So next we're going to prove one of the Baker-Campbell-Hausdorff formulae. So this is not the most general one, but this is the one that we used in the lecture. So Hausdorff. There are a few other names that I forget, so this was derived by many people independently. And the idea is that whenever we have two operators A and B which do not commute, how do we make sense of products of exponential of these operators? How do we evaluate something like this? So what we're going to do is that we are going to evaluate a certain version of this. We are going to evaluate e to the power, say, a or minus a, b times e to the power plus a. We're going to evaluate this. So to evaluate this, what we do is that we first define a function of t. It's a matrix function, and it's given by e to the power a times t. So t is not a matrix, it's a parameter, it's a real parameter, times b e to the power minus a of t. So, and then we can take derivatives of this function with respect to t. And if we do this, then, what we're going to do is that the first term is going to, bring down a factor of a, and then there's b, and then e to the power minus at. And the second term is going to bring down a factor of minus a, but that minus a will be after b. So this will be, so we can write this as e to the power at, the commutator of the commutator of AB times e to the power minus at. So now similarly we can do a second derivative of f, and the second derivative of f will give us e to the power at, a nested commutator of a and with b, and then e to the power minus a. So if we, and we can keep on doing this, if we do nth derivative here, then we are going to get a factor of e to the power at, and then we are going to get n nested commutator of a with b, e to the power minus a of t. So now what we can do is that we can say, okay, what is the function f of t? Of course, this is a completely well-defined function, although it's a matrix function. So we can apply Taylor series to it. So the Taylor series expansion of this function around the point 0 is going to be f of 0 plus t f prime of 0 plus t squared by factorial of 2 f double prime of 0, so on and so forth. And so if I look at f prime of 0, what happens is that these guys become, these factors e to the power at and e to the minus at, they become 1, and all we're left with is the commutator. So for higher derivatives of f, these exponential factors vanish, all we're left with are commutators. And therefore what we have is that as a result, we just get this is going to be equal to, say, the first term will be b, and the second term will be just t times commutator of a and b, and the third term would be t squared by factorial of 2, commutator of a and commutator of a, b, and so on and so forth. So if I look at then the function f and evaluate it at t equals to 1, so let us look at the definition of f. So here we are putting t equals to 1. So that means that this will be given by e to the power a times b e to the power minus a, and that becomes a summation, a power series, a summation over n, and all the t's have been set to 1. So all we have here is 1 over factorial n, and then for each given value of n, we will have n nested commutator of a with b, and this is one of the, so this thing is one of the BCH, Baker-Campbell-Hausdorff formula. And in the lecture we used the case where basically b was 1 and a was, say, some I times h, and as you can see, here b becomes 1, so all of these right hand side, it just boils down to 1.